This is part one for quantum physics. What is quantum physics? Now, quantum physics is going to deal with the physics of particles. We may have heard the term of photon. We may have heard the term of quantum first, or previously before coming into physics. But what is it actually? What are we looking for? What is the basic idea? And what are the you can say, concepts required for this chapter to be completely acceptable in terms of an A-level student? So I'm going to keep things simple and straightforward. If you want to go into detail, you can search each individual topic that I'm going to teach on YouTube as well. But I'm only going to limit this lesson to what type of questions the examiner is going to ask you. And what I have observed is the expectation of the examiner from this chapter. So moving on to the first point, that is energy and momentum of a photon. Understand that electromagnetic radiation has a particulate nature. So what is that particle? What is the name of that particle? The name of that particle is a photon, which point number one and point number two will be covered in the points that I'm going to discuss now. So we imagine that electromagnetic radiation, and when I say electromagnetic radiation, yes, we are talking about gamma up to radio. We are talking about the complete spectrum. But in this lesson, you will see that I will frequently refer to the visible spectrum just because of the convenience of visualization. Because we can see it, we can observe it. That's all. Otherwise, whatever rules apply to this visible spectrum, and for the purpose of this lesson, they will be equally applicable from gamma up to radio. Keep that in mind. Okay. Now we have observed that these are actually traveling as waves. But quantum physics tells us, and a few experiments that we've conducted tells us, that wave is okay. Wave is one side, but these radiations are also actually traveling like in terms of packets of energy. Packets of energy, which we call as particles, and we refer to them as particles, and photon is that name of that particle. We've given that packet of energy, a small quantized packet of energy, the name photon. So what is the energy of a photon? So when we're talking about this visible spectrum, we believe that from, let's say, a torch or a light bulb, whatever source we have right now, for example, if we have a bulb, right? If we have a bulb like this, the radiations coming out of this are in terms of waves when it moves through matter, but when it interacts with some surfaces or matter, it actually behaves like a particle. This dual nature will be explored in the second part of this quantum physics, but for the sake of understanding, let's keep this in mind, that photons are packet of energy. Now, next, he wants us to get familiar with the concept of E equals to hf. So what is the energy of a photon, and how do we know that it is equal to this? So energy of a photon is proportional first. The first thought is proportional to the frequency of the radiation. That is why we refer that X-rays and gamma rays are highly energetic. Why? Because they have very high frequency. That's why they can penetrate through matter without losing much of the energy. That is why they cause cancer. Okay. So when we convert this proportionality to inequality, we need to involve a constant, and in this case, that constant is Planck's constant. So Planck is the person who actually identified this in the first place, this relationship between energy and frequency. So what does this tell you? It tells you that if you put in the value of Planck's constant, and you multiply this with the frequency of radiation, yes, starting from gamma rays up to radio waves, whatever frequency that you have in hertz, you will find in joules the energy of that photon. The value of Planck constant is usually given in the data booklet, and that is 6.63 into 10 raised to power minus 34 joule seconds. Okay. All right. So I will choose the frequency of my whatever I want to find the frequency of, whatever I want to find the energy of, and I will put this as formula, and I'll find the energy of that photon. Now, when we do that in physics, we find out that the energy comes out to be very small. Okay. That generally ranges to the power of minus 19, ranges from minus 20 to minus 15, let's say, joules. Now, dealing with this prefix becomes inconvenient. So what we've done, we've developed a new unit for energy, which I will discuss in the second part of this video. Okay. So these are the common things that you've already done in physics in terms of wave nature, how wave behaves like a wave. This radiation behaves like a wave. So the common experiments that you've already done are sound, the pressure changing between the rarefaction and compression, light moving as an electromagnetic radiation, electric field and magnetic field. I've also shown this animation in A1's video as well. Waves on a string, displacement, their individual displacement, and some common things as diffraction, refraction, reflection, interference, polarization, which we do everything in A1 waves. These experiments are purely based on waves. What do we mean by this statement? We are trying to say that when light is subjected to all these experiments individually, they satisfy the outcome. Whatever we are expecting, it does come on the outcome. It undergoes diffraction, it undergoes refraction, it undergoes reflection, it undergoes interference and polarization. These qualities, these experiments are only applicable, or only they only show result when the thing that we are testing is actually a wave. But when we move towards the particle model, we realize that in electricity, we have flow of electrons, individual packets. In gases, we have kinetic theory, that gas molecules have a specific size, specific shape, and that's how they're responding. In solids, similarly in radioactivity and chemistry as well, the atomic structure, of course. But in A levels physics, at least quantum physics, we will see that there are discrete energy levels. There is a photoelectric effect, and there is line spectra, which is quantum physics part 2 of this video. I will not explore them in this video. We are going to explore the basics of quantum physics, and then we'll go to these experiments. So previously I was telling you that there is an inconvenience in terms of values, in terms of dealing with values. So how we have bypassed this, we're going to make a new unit of energy that is going to make our calculations easy. So the new unit is called electron volt. How do we come about this? We go back to the basic equation of voltage, which is volt is equal to work done by charge. This is AS electricity. So when we make Q, we take Q over there, QV equals to work done. Now this work done is actually joules. So what we've done, we are visualizing that between two plates, for example, one is positive, one is negative, connected by a high potential voltage DC supply. So if there is an electron, let's say at this one point, if it is accelerated towards the positive plate because of these charged plates, so that work has been done by this battery with a voltage V. And if we know the charge of this charged body, then if we multiply this charge with the accelerating potential voltage V, we can find out the energy subjected or injected into the system. So we can specifically, you can say that work done equals to the energy given to the electron is equal to QV. Now, for the sake of example, if we say that we are dealing with just 1 volt of voltage, and the charge that we are compensating, that we are trying to move through this, is actually an electron or a proton with a unit charge of 1.6 power minus 19. So if you put these values into this actually energy comes out as 1 volt multiplied by 1.6 into 10 raised to the power minus 19. This comes out as 1.6 into 10 raised to the power minus 19 joules, because this is equal to energy. Now, what do we do with this unit? Again, as I told you before, that we are actually going to get a power of 19, 22, and 15. We're going to make a new unit for ourselves, and that unit will be called electron volt. So what we're going to do, we're going to say that 1 electron volt, which I put over here, that this was 1 volt, this was 1 charge, is actually equal to 1.6 into 10 raised to the power minus 19 joules. So what I will do now is I will calculate this one equation. For example, let's say we want to find out the photon's energy that is actually at a frequency of 6.63 minus 34. Let's calculate the energy for photon that is at a frequency of, or let's involve a new thing. Let's say that it is a lambda of 700 nanometers. Now what do we do with this? We know the equation V equals to F lambda. We know that over here we need F. So I will make F the subject of the formula, and we'll get V divided by lambda. So over here I'm going to write down the speed of light, which is 3 into 10 raised to the power 8, divided by the wavelength, which is 700 nanometers. For God's sake, please make sure that you convert these powers to the respective answer. Now, please try this on the calculator and get back to this. The answer that I'm getting is 2.7 into 10 raised to the power minus 19. As I told you before, that these will be the ranges of answers. Again, dealing with minus sign is a problem. So what I'm going to do, I'm going to divide this with 1 electron volt energy, which is a standard value 1.6 minus 19 joules per electron volt. So when I do that, I get an answer of 1.6875 electron volts, which up to two significant figures will be written down as 1.7 electron volts. So now dealing with this number, which is 1.7, is much more easier in comparison to dealing with this large number in terms of small decimal places. That's all we have done with electron volt. This is the only purpose of this concept. The next thing is about, okay, so let's go back to the syllabus and take this off. So we understand what is electron volt, what is the purpose of this equation. Understand that photon has a momentum, and that momentum is given by this formula. So previously we have understood, we've discussed that if you need momentum, for example, if you need momentum from AS physics, from A levels 1, you need to have a mass and you need to have a velocity of a particle, of a mass, of anything. But when we come to light, we can't measure its mass. There is no mass. Electromagnetic radiation does not have a mass, but it still has a momentum. And why is that so? You can explore this online as well, that when any radiation or any physical object tries to reach the speed of light, most of its energy, most of its mass actually converts into energy. So the more you approach the speed of light, your mass is eventually converted into simple energy. So based on this idea, we can backtrack our way that if light has energy, which we have experienced, if you stand in the sun, your body starts heating up. If you have a metal piece in the sun, or it's lying around the sun, it heats up as well. So if light has energy, then it must have a mass. But we can't do that right now because light doesn't have a mass. So what we're trying to justify from this is that light or photons must have a momentum. So we try to justify this momentum by a simple mathematical equation, which is going to look like this. That if we are approaching the speed of light, for example, then the energy of any system is actually equal to mc square. And since we're dealing with the energy of a photon or a particle, we can equate this to E equals to hf as well. But we don't require this part of the system right now. We only require this part. So this energy is equal to mc square. If I separate this equation as mc dot c, it doesn't matter. I've just opened this up mathematically. Let's take the c over there. This becomes E divided by c equals to mc. Now I know that m is mass and c is the speed of light. And when I see that the momentum formula is mass multiplied by velocity, I can simply replace this over here, and the equation that I get is E divided by c is equal to momentum of the photon. So if I calculate the energy of a photon by the formula of hf, I replace it in this formula and divide this with the speed of light, I will get the momentum of a photon. And if you want to explore this further, you can go on and read about radiation pressure. Radiation pressure. You don't observe this in daily life, but when, for example, if you're standing in the sunlight, this radiation is traveling towards you as photons, as packets of energy. When they collide with your skin, they are exerting a force because they have a momentum, and we know that force is defined as rate of change of momentum from A1 physics. So when there is a change of momentum, for example, the photons are coming on your skin surface, they are absorbed, their momentum changes to 0. So there is a very large change in momentum in a very short amount of time. So they exert a very large force. But in terms of the negative power of 19, because we're dealing with very small entity, and the energy and the values and all these radiations are actually going to have a value of minus 19. So that actually is not felt by you on your skin, but this exists. This actually plays a role in star formation as well. When a star is actually being formed, what is the outwards push by the star? What is this? This is not only just the explosive energy of the radiation, this is also radiation pressure. And what is trying to pull the star inwards? It's gravitational attraction. So when these two things become equal, we say that a star is formed. That's exactly how our sun is actually behaving. Its light, its radiation alone generates so much outward pressure that it is actually compensating the gravity that is trying to pull it downwards. So this radiation pressure is an important thing. Okay, so we understand the momentum equation given in the syllabus as well. Also, from this concept, we also make one equation that if work done into the charge was QV, and if that is going to produce a kinetic energy in this moving charge, then let's equate both of them. So this is half mv square. The velocity of this particle, of this charged particle, is going to be 2ev divided by m under root. Now, when you go to higher physics, you realize the importance of this ratio, charge to mass. You will find everything as a ratio of charge to mass, especially in chemistry and mass spectrometry. You see, in higher levels physics, we realize that it is difficult to measure the charge and the mass of a very, very small particle. So how do we gauge which particle are we dealing with? Are we dealing with an electron? Are we dealing with a photon? Are we dealing with a proton? Are we dealing with a neutron? How do we know this? We know them by their charge to mass ratio. Under special situation, under special circumstances, at certain voltage, certain velocity, they will produce a certain path. So you can also research about this as well. Okay, so momentum of photon, we've done that from the part of the syllabus as well. We have proven that the energy divided by speed of light is going to be the momentum of light. So now, where does it all end? Where does it actually going to, where is it taking us? What is the topic that we're interested to find? We're interested to study about the photoelectric effect. Now, there are going to be some rules, there are going to be some observation. Let's go through all of them. So first he says, understand that photoelectrons may be emitted from the illuminated surface. Understand the use of threshold frequency. Let's see what is photoelectric effect. From any metal surface, could be copper, could be zinc, could be aluminium, could be brass, could be any alloy. It does not matter. It doesn't matter. But for the sake of simplicity, we're just taking one metal. We're not taking an alloy. What we've observed is that if radiation is coming in terms of photons precisely, we're not thinking about waves because we have done waves in A levels or in A1. Now we are thinking about quantum physics. We are thinking about quanta. We are thinking about particles. So when these photons arrive on the surface of this metal surface starts ejecting electrons. And if that energy, okay, so we'll get to that later. So this incident light, which has photons, starts causing these electrons to get emitted. This is known as photoelectric effect. Okay. Now there are going to be some factors, there are going to be some physical factors that we're going to change and see what's going to happen. Let's see what those are. So what is threshold frequency? Threshold frequency is the minimum frequency required by the light or the incoming light on the metal surface that is eventually going to successfully cause the ejection of an electron. You see, I know that this photon that is arriving has to have a certain energy, which is HF. So this F will be known as threshold frequency. But when will I call this threshold frequency? If this energy or if this frequency produces enough energy that this electron needs to escape, primarily ionization energy, which you have done in chemistry as well. To eject or to remove an electron from a substance is ionization energy. So if this photon doesn't have that, then the electron will not go out. It will not come out. If it is higher than that, or if it is equal to the threshold frequency or the requirement of the photon, then we will call this as threshold frequency. We'll introduce more terms in this as well. But what happens if this energy is not enough? What happens to the electron? So the metal starts heating up. If this energy is not enough, the metal will start heating up. This is what happens with you when you go out in the sun. When you're standing out in the sun, the radiation coming from the sun doesn't have the photon that is going to cause an ejection of electron from your skin. So what happens instead? The energy of the photon is taken by the electron, but the electron is unable to escape. So what happens? The electron comes back to the original state. It comes back. It tries to escape, but it comes back. But it gives its energy to the positive ion, which actually is holding all the electrons together in terms of chemistry. So where does that energy end up? It starts heating up the metal itself, or it starts heating you up if you're standing in the sun. So let's visualize how this is actually going to function. So I send in a certain energy photon, and these electrons are going to try to come out of this or try to get ejected from this by gaining this energy. Okay. What if this energy is not enough? The electron tries to escape, but if the energy is not enough, it comes back again. Why is this energy not enough? Because there is a possibility that the positive charge at the center, the nucleus, is attracting all these electrons from different shells that we have in the electron shells. So for this electron to escape, it needs to overcome the positive attraction of the nucleus. So that energy that is required to overcome this attraction, to overcome all the factors, is known as phi. And what is this phi? This phi is called work function. So work function will be the minimum energy. Most definitely this is in joules, but we're dealing with smaller units, so it will be given in electron volts. No need to worry about that. So the minimum amount of energy required to make sure that an electron is ejected from the surface. Now, there are two situations in this. Electron will barely manage to come out of this. For example, if the work function energy is 10 joules and you bring in a photon of 9 joules, the electron will try to escape but will unable to do so. It will come back and cause heating of the metal surface. What if you provide this such a photon that has 10 joules, exactly what the electron needs? The electron will absorb that energy and just barely manage out of this metal surface, but it will have no kinetic energy. It will not be moving. It will just be stationary near the surface of the metal. What if the third and the last case? What happens if you have more energy than what is required, than the work function? Let's say you bring in a photon that has 15 joules and the work function is 10 joules. What's going to happen? You may have guessed it correctly. The 15 joules, out of 15 joules, 10 joules will be utilized to overcome the work function, and 5 joules would translate into the kinetic energy of the electron. So this equation actually becomes something like this, that the energy of the photon is equal to the energy of the electron that is actually going to get emitted. Now, where is this energy going to end up? Where is it going? According to the law of conservation of energy, energy before and after should remain the same. So from this idea, we make this equation that HF is the photon that brought the energy into the system. It should be equal to the work function at least to cause photoelectric effect. And if something is extra, that energy will show up as the kinetic energy of the photon. If the photon barely managed to cause this electron to eject, then the kinetic energy will be zero. It's fine. It doesn't matter. If it is less, it will cause metallic heating. Okay. All right. So going back to the syllabus, let's see what we've covered. So we see that a metal will release electrons. We understand the term threshold frequency, threshold wavelength. We understand that photon energy and the work function, how they are actually linked. We understand this equation as well. Photon energy compensating for work function and extra energy translating into kinetic energy. Now, last point is going to require a bit of detail and discussion. That will be the last part of this lesson. He says that the maximum kinetic energy of the photon is independent of the intensity, whereas the photoelectric current is proportional to intensity. Now, this is a confusing statement. Don't worry about it. We're going to discuss it. So, what is he trying to say? Let's try to simplify this. He says that on a metal surface, for example, when you are introducing this photon radiation and you're expecting electrons to come out, okay, the intensity will not matter. The intensity is not controlling anything, but it is controlling one thing. Let's see what that is. So first we go back to A levels 1, AS. We first try to understand what is intensity. We understand that intensity is watts per meter square or power per unit area, but let's try to make it simple in terms of quantum physics. Intensity would mean number of photons being received by the metal. Be careful about this idea. Now, if all the photons that you're receiving on the metal surface, for example, this is the metal surface, all the photons that you're receiving on the metal surface, let's say that I am sending in 10 photons. Let's give them numbers to make it easy. I'm sending in 10 photons and each one of them has 9 joules of energy. But the work function required is 10 joules. The electron needs 10 joules to escape, otherwise it cannot escape. What's going to happen? It is going to cause metallic heating. Now, if I increase the intensity, what is the intensity? The number of photons. Even if I make 20 photons, even if I provide 1000 photons at this surface and all of them having only 9 joules of energy, according to the idea of E equals to HF, no matter what you're trying to do, electrons will not escape. Right? So increasing intensity does not do anything. if your energy requirement is not equal or greater than the work function. Now let's change the scenario. Let's say that we are providing a photon that has the work function. Let's say it has 10 joules. Okay. Now 10 photons are going to produce 10 electrons. We will see why that is the case. Because only one photon is responsible for ejection of one electron. Because the energy is only good enough for one electron. And even if it is greater, it will only be consumed and taken by just one electron. Okay, so if this energy matches, then now I can experience at least 10 electrons coming out of the metal plate. Now, what are these electrons? I can call them current. I can call them or refer to them as electric current because they're moving in the same direction. Okay. Even if they're scattering, I could refer to them as current. Now, let's say you provide 1000 photons by increasing the intensity, because intensity is the number of photons received. Now, let's say there are 1000 photons coming on the surface. First, we will need to check whether the work function energy is being satisfied. Yes, it is. Now, these 1000 photons will cause the ejection of 1000 electrons. So now the intensity matters. Previously, the intensity did not because the work function was not breached. Now, if the work function energy is being compensated by the photon, or at least the photon energy is greater than the work function, now the electrons will increase. In these circumstances, we can say that the intensity of the radiation will control the photoelectric current coming from the surface. Only when you cross the threshold frequency, if the frequency is actually being, you can say matched or at least crossed, because we know that if the frequency is higher, then the energy of the incoming photon will be greater. Now let's consider another scenario in which I have seen the question asked from the students as well. Let's say that we are not going to change the energy of the photon. We are going to change the number of, we are going to keep the number of photons constant, but we're going to increase their energy. Let's say that the work function in this case is still 10 joules. The electron requires 10 joules to escape. It needs that much money. It needs that much energy to overcome the attractive forces of the nucleus. So let's say we're going to consider two scenarios. Scenario number one, blue colored, we have 10 photons having 10 joules. And then we're going to consider a green case in which we have 10 photons. You see, previously what I did, I changed the number of photons from 10 to 1000 and the current increased. Yes, it can. But this time I'm providing a photon that has 15 joules of energy. In a third case, for example, I provide 10 photons, still the same number of photons, but with 25 joules of energy. What's going to happen? You can take a guess. Okay, so what happens with blue? You see, you send 10 photons, you barely receive 10 electrons because they will have no kinetic energy. Why? Because the equation is simple. HF equals to work function plus kinetic energy. You barely manage to provide the energy to escape it. Will it have something extra to spend or have to move out of there or to have some kinetic energy? No. So what is the second case? We have still the same radiation, same intensity, same photons coming in, but now they have 15 joules, which means I can split this into 10 plus 5. 10 joules required for work function and 5 joules extra for the kinetic energy. So these electrons will be moving at a higher speed, but remember they are still only 10 electrons. Why? Because we are following a one-to-one function, one photon responsible for one electron. This is the beauty of quantum physics. Because if this was a wave, like we do generally in experience in daily life as well, you keep something in the microwave to heat it up. What happens after some time? As the time passes by, the energy of the microwave gets added into the food and it heats up. In quantum physics, this is not the case. You see, you have to provide at least the work function, otherwise nothing is going to happen. Right? So that is why we say that this light radiation is actually behaving like a particle, is actually a quantum, is actually behaving like a packet of energy. Okay, this is a debate for another day. So what's going to happen now? Now, since they have more speed because the kinetic energy is higher, I will experience that the photoelectric current will increase. Why? Because current is actually flow of charge per unit time. And if you go to AS, if you go to A levels, then that is NAQV, certain velocity, charge density, cross-sectional area charge. So if you talk about higher current, Obviously, we can see that the velocity has increased. So although the number of electrons are same, the charges are same, but they're traveling at a higher speed, so they will be moving with less time. The same journey will be completed in less time. So the current is going to go high. What about the third case? In the third case, exactly similar like the green one, but this time it's going to go at an even higher speed, because if I split this down to 10 plus 15 to make 25, 10 used for phi and 15 used for half mv square. You see, previously I had a budget of 5 joules to provide the kinetic energy. Now I have a budget of 15 joules. I can use 15 joules, or the electron can use 15 joules to get out of this. So it used that energy and raced away at an even higher speed. Now we know that if the speed increases or the drift velocity increases, the current increases. And this will again call for a higher photoelectric current detected in the ammeter. So although we are not changing the intensity, we are changing their energy. We are providing a high energetic photon that will also call for an increase in the photoelectric current. But in both cases, we need to cross the threshold frequency. We need to provide the work function energy. Only then these things become proportional. Higher intensity, more current. More photon energy, more current, or higher current. Okay, this is the confusion set up by the examiner. Now let's come down to this idea. This is a summary of the photoelectric effect, and these points should be known by every A-level student at least. So the velocity of the electron is independent of the intensity. This is what we discussed. If intensity does not matter, what matters is the threshold frequency. If you cross the threshold frequency, then increasing intensity increases the current. Second point, photoelectric current is proportional to the intensity of light. Okay, so this is the confusion. First, he says that it is not dependent on intensity. Now he says it is. It is only dependent when you provide the work function. Third part, for a given metal, certain maximum threshold should be, okay, electrons stop completely. This frequency is the threshold frequency. Yes, we've discussed the threshold frequency as well. So photoelectric emission is an instant. This is important. This is not called for. It is instantaneous. In waves, if you stand in the radiation, if you stand in the sun, your temperature starts rising slowly, right? It is an addition of the energy of the radiation coming from the sun. You will not experience this in quantum physics. And what is happening in the quantum physics? Does the electron wait for the particle to escape? Let's say if I introduce a photon with a certain HF energy, will the electron first wait and then escape? No, it will instantly escape. It will not wait for a second. This instantaneous process, this process being instantaneous, is the guarantee that we are dealing with quantum physics. We are dealing with particle physics at a quantum level. See, if this was a wave, it would have taken some time to heat up, just like we are cooking food in the microwave. It would take some time. Here, it does not. Plus, the fifth important part is that it is a one-to-one function. One photon releases one electron. No matter its energy, high or low, it will only be responsible for ejection of one electron. This is again a particle behavior. If this would have been a factor of wave, let's see if this was wave. You see, even if I'm sending in an electron or a photon with 9 joules of energy, why is this electron so stubborn that I need 10 joules to escape? Why can't it wait for another photon, let's say 9 joules, take this 9 joules, absorb this, and wait for the second photon to come in and provide more 9 joules? Now it has 18 joules. No, this addition of energy is not possible for photons. This is not possible for particle physics. This is where the discrepancy starts to take place. This is where we see the dual nature of light. This addition of energy is observed by waves, like cooking food, standing in the sun. But when it's about particle physics, when it's about quantum physics, light behaves peculiarly and only deals with this electron if you cross the threshold frequency by providing a certain photon. I hope that it has intrigued your interest, that sometimes light is doing something else, sometimes it's doing something else, and it is counterintuitive to both sides. That is the dual nature of light, which I'm going to explore in the second part of quantum physics.